So in this video we're going to just justify the surface area of revolution formula in polar form and kind of show how we can derive or come up with that. So remember in a previous video we came up with the surface area formulas for surface areas of revolution if we were working with parameterized functions, x equals f of t, y equals g of t, and these were the two formulas that we came up with. This one corresponded to an x-axis revolution, and this formula corresponded to a y-axis revolution. So what we want to recognize is that this term right here in the surface area function, as we've already mentioned, this term right here is the arc length. This is just the arc length. And we know if we're working in polar form, we have radius equal to some function of theta, and we know that we are able to parameterize this because we already did it. We said, hey, x of theta is the radius times the cosine of theta, and that just comes to us from trigonometry, and y of theta just equals the radius times the sine of theta, which comes to us from trigonometry. So we can parameterize, if we have a polar equation, we can parameterize it using these relationships from trigonometry. And the moment we do that, we can apply this directly to those parameterizations, and we did that in 2 videos ago. We actually did this parameterization process and came up with the arc length formula in polar form, and what we discovered was that we could calculate the arc length, which is what this piece is. We could calculate it by taking the square root of the radius squared plus the derivative of the radius squared d theta. That was derived by parameterizing the curve when we had a polar representation and doing some manipulation and simplification. And of course, if r is equal to f of theta, we could replace the r and the r prime with r. We could replace it with f and f prime just as easily. So then we need to think about in the surface area of revolution formula what else was going on besides multiplying by arc length. Well, we have 2 pi times the radius. G of t is just the radius. When you do the x-axis revolution, and we've already talked about this, x-axis revolution means that your radii, which is just the distance from the x-axis, geez, I'm having a hard time with the eraser tonight. The radii, which is just the distance from the x-axis to the curve, those are going to be the y-coordinates on the graph. The height, or the y value, is the radius. So if we have a parameterized function y equals g of t, then the height, or the y value, is just g of t. It's 2 pi times the radius. But if we're converting over to polar form, we know that the y value is the radius times the sine of theta. So what we would do is replace the arc length with the arc length in polar form, and then we would just replace the radius with which is the y coordinate. This g of t is just y. You replace the y coordinate with r sine theta. It's that straightforward. And instead of running over t's, you're going to be running from some theta naught to theta sub 1. And that's how you would generate that formula. So again, down here with the y-axis revolution, you're revolving some curve around the y-axis, means your radii are the distance from the y-axis to the curve, but that's just the x-coordinate. And so this f of t here is coming from, that's how the x-coordinate, or the distance from the y-axis, is being described. 2 pi times the radius. What's the circumference? And then the circumference times the arc length. So again, you just replace the arc length with the derived arc length in polar form. So you get r squared, r prime squared d theta. There's the arc length in polar form from 2 videos ago. And the radii are going to be the x-coordinates, but we know how to parameterize the x-coordinate as a function of theta. It's just equal to r cos theta. And you run it over the appropriate theta interval, theta naught to theta sub 1, or alpha to beta if you want to call theta naught alpha and theta sub 1 beta. You run it from alpha to beta. So it just comes, the polar form of the surface area of revolution just comes from taking the parametric form and realizing that you can parameterize the polar form and substitute the appropriate pieces into the parameterized formula. And so this just summarizes what we just talked about. Hey, if you're revolving around the polar axis, which is the axis that overlays the x-axis when we superimpose the two coordinate systems. So this, well, you want to think about this as a x-axis rotation, and the line theta equals pi over 2 would be your vertical axis, which when you do a polar coordinate system, you could overlay on top of an xy coordinate system. So there's the formulas. I'm not going to do any examples of applying this, because when you apply this formula, you really just are relying on techniques that you've already developed.